Imagine a hidden engine beneath Earth's oceans, a massive conveyor belt made of water that brings warmth to distant lands, regulates weather systems across the globe, and stabilizes the very climate that human life depends on. This engine has been running for thousands of years, quietly shaping temperatures, rainfall, storms, and the survival of ecosystems. But now, scientists believe this giant system is losing strength. What if I told you that this weakening could rewrite the world's climate map? That centuries of stable weather patterns, predictable seasons, bountiful harvests, and comfortable human settlements might begin to unravel? That places known for mild winters could face brutal cold? That coastlines could rise faster than we ever imagined? That storms could become fiercer and rains could shift to droughts? This isn't a sci-fi blockbuster. This is Earth's reality. Today, we're talking about the Atlantic Meridional Overturning Circulation, or AMOC, a vital system of ocean currents that behaves like the planet's heart pumping heat across the globe. New data from decades of ocean measurements and climate models suggest that this ocean engine is losing speed, and if it weakens further, the consequences will be nothing short of terrifying. But to understand how massive this threat is, we need to go inside the engine itself, what it is, how it works, why it's slowing, what could happen next, and why scientists are both worried and cautious. This story is about oceans, climate, civilization, and why the next few decades matter more than we ever realized. When we talk about the Atlantic current slowing down, what we're really referring to is a vast interconnected system of ocean currents called the Atlantic Meridional Overturning Circulation AMOC. What AMOC is? The AMOC is a giant conveyor belt of water, a network of currents in the Atlantic Ocean that move warm surface waters northward and cold, dense waters southward at depth. Warm water from the tropics travels north along the surface, including the well-known Gulf Stream. As it reaches northern latitudes, especially near Greenland and the Arctic, it cools and becomes denser, especially because saltier water weighs more than fresh water. This dense water sinks deep into the ocean and flows back south, completing a massive loop. This circulation helps transfer heat from the equator toward the poles, dramatically influencing climate. Europe, for example, receives much warmer conditions than other regions at similar latitudes because of this flow. How it works? The system depends on two key physical forces. Temperature differences, cold water near the poles is heavier and sinks. Salinity differences, saltier water is denser than fresher water. Together, these create the thermohaline circulation, literally driven by temperature and salinity. This isn't a small flow. Scientists measure the AMOC in sieverts SV, where 1 sievert equals 1 million cubic meters per second. Roughly 12 to 25 sieverts flows through this system at any given time, an unimaginable amount of water. Why Earth needs this conveyor? Without this circulation, heat distribution around the globe would change dramatically. European Union emoji, Europe would be much colder than it is now. America's emoji, global rainfall patterns, from the African Sahel to the Indian monsoon, would alter. Ocean wave emoji, oceans would absorb less carbon dioxide and heat, speeding Earth's warming. These currents are a cornerstone of the planet's climate system. Scientists have debated for decades whether the AMOC is slowing. There are three sources of evidence. 1. Historical temperature salinity data. Studies using long records of ocean temperature and salinity patterns have found consistent signs pointing toward a decline in the strength of the circulatory flow. In fact, pushpin emoji, some centuries-long reconstructions suggest the AMOC has weakened significantly since the mid-20th century, potentially by 15% or more compared to its strength 1,000 years ago. This weakening is indicated by a persistent cold patch south of Greenland, paradoxically cooler even while the rest of the ocean warms, which fits what we'd expect if northward heat transport was diminishing. 2. Freshwater heat models Greenland meltwater. One of the clearest explanations scientists have identified is the influx of fresh meltwater from Greenland and Arctic ice. As the planet warms, ice sheets melt faster, pouring freshwater into the North Atlantic. Freshwater is less dense than salty ocean water, so it disrupts the sinking of cold, salty water, the very force that drives the AMOC. If less water sinks, the circulation slows. 3. Direct observation scientific debate. However, there's a twist. A major 2025 study using direct measurements of air-sea heat exchanges found no clear decline in AMOC over the past 60 years, challenging earlier claims. So is it slowing now, or will it slow in the future? Right pointing finger emoji. Many scientists agree that long-term slowdown is likely, even if short-term trends are uncertain. Even experts who argue the current isn't currently weakening still warn a slowdown is coming as warm air, melting ice, and shifts in salinity continue. Here's why the possibility of a weakening AMOC is terrifying. Cold face emoji. 1. Plunging European temperatures. One of the most dramatic consequences of AMOC weakening is the possibility of cold spells and freezing winters in Europe, not global cooling, but regional anomalies. Because Europe's relatively mild climate depends on heat brought north by the AMOC and Gulf Stream, losing that heat source would allow colder Arctic air to dominate. Cities like London, Paris, Berlin, historically warm compared to similar latitudes, could face bitter winter conditions. Some models suggest much colder winters and more severe storms hitting Western Europe. Rain cloud emoji. 2. Shifts in global rainfall patterns. Drought. The AMOC also influences atmospheric circulation patterns, including the location of the Intertropical Convergence Zone (ITCZ), which sets tropical rainfall belts. If the AMOC weakens, the African monsoon could shift or weaken, intensifying droughts across the Sahel and West Africa. The Indian monsoon could become less predictable, threatening water supplies for billions. South American rain patterns, including Amazon rainfall, could shift dramatically. This would impact agriculture, freshwater supplies, and ecosystems on multiple continents. Ocean wave emoji. 3. Rising seas along U.S. East Coast. Another hidden consequence of a slowing AMOC is regional sea level rise. The circulation slows, water piles up along the U.S. East Coast, amplifying sea level rise already caused by thermal expansion and melting ice. This threatens coastal communities, infrastructure, and millions of people from Florida to Maine. Ecosystem disruptions. Oceanic oxygen loss. The circulation helps bring oxygen-rich water and nutrients to deep ocean ecosystems. If it weakens, deep sea ecosystems could lose oxygen. Marine life patterns could shift. Fisheries could collapse in some regions. The climate system is full of feedback loops. A weakened AMOC could reduce the ocean's ability to absorb heat and carbon. Less heat absorption by oceans means more warming in the atmosphere, accelerating global climate change. Is a total collapse inevitable? Not yet. But models show that if greenhouse gas emissions continue unabated, the AMOC could approach a tipping point, beyond which it might shift to a much weaker state or shut down altogether. Intergovernmental Panel on Climate Change (IPCC) assessments and recent research indicate that. Checkmark emoji. Even without a full collapse, a dramatic weakening would have huge impacts. Checkmark emoji. A collapse, while debated, is considered within the realm of possibility this century or next, depending on emissions. Rather than a sudden flip, scientists warn of a long-term sliding decline, where incremental slowing produces bigger climatic effects over decades. One reason scientists disagree: measuring AMOC directly is extremely difficult, and proxies like sea surface temperature and salinity provide indirect evidence. That said, geological records show that AMOC has collapsed in the past, triggering sudden and dramatic climate shifts. For example, at the end of the last ice age, abrupt freshwater influxes appear to have caused collapses that plunged northern climates into deep cold spells lasting centuries. What must we do? So what's the takeaway? Slowing of the Atlantic current is not a guaranteed apocalypse tomorrow, but it's a serious climate risk, one that could worsen as Earth warms and ice melts. Sparkles emoji. The single most effective way to avoid the worst outcomes? Cut greenhouse gas emissions drastically. Reducing emissions limits warming, slows ice melt, preserves salinity balance, and buys time for adaptation. Scientists argue this is urgent. The longer we wait, the closer the system edges to irreversible change. The Atlantic current isn't just a river in the sea, it's a planetary heat engine, a regulator of weather, a foundation of climate stability. Its slowing is a signal, not just of change, but of a world pushed beyond boundaries established over millennia. Whether this becomes a crisis or a wake-up call depends on our actions now. Climate science isn't about fear, it's about understanding risk, probabilities, and thresholds. But ignoring this silent shift beneath the waves would be a mistake we can't afford.